The second law of thermodynamics says that the entropy will keep rising. The entropy is basically the disorder or randomness. As you can see, it's true for my workbench. Brian Cox put it this way: everything goes to shit, and that is true here. As you can count, there are 3 motors now. There's 1, 2, and there's 3. This was the original one on my CNC, and that basically burnt up. Then I bought a second one, which was also burnt up. And then I bought a new one, which is not burnt up. Welcome back to the shrine. If you haven't seen that previous video, check it out. I did a teardown analysis for this motor. This is a servo motor from my CNC mill, and it's a complex system. It's got a DC motor, it's got a DC tach, and it also has an encoder. So the tach and the encoder seemingly work, but the motor is burnt up. So I looked up the part number and went on eBay, found the same part number. There were actually 2 motors for sale. One's for $150 and one's for $750. And I picked this one because this was just 2 hours away from where I live, and the seller said they cannot test it as is. I was fingers crossed. I ordered it, delivered it, and it's burnt up. The motor is burnt up, not as bad as this one. I also hooked it up. It works, but it's drawing too much current, and every once in a while it will trip the breaker on my bench. So I kept searching and I found a third one. So you can see this is called Enelum Electronics, but it's being made by the same company. It's SEM in London, England. And it is working. There's just a couple minor issues with it, which I summarized right there. So the original part number is MTS 30M4-59, and I couldn't get that. So again, this is the original one. The second one was the same part number, as you can see right there. And then this one is MT 30M4-59. So if we compare them side by side, you can see that this is a longer motor, and the termination comes out to the side. There's actually a terminal box sitting right here that I removed. Okay, and that's where the cable comes out. Now the original one has this cover, and the termination is on the side, so that's where the cable come out. So that's not a big problem, right? I mean, we can just wire it up and see how it goes. One of the questions, if the motor voltage and the tach voltage at 1000 RPM matches this one. Okay, so when we apply 59 volts DC, the motor should be spinning at 1000 RPM, and the tach should give us 9.5 volts. So you can see it's right here. So at 1000 RPM, 59 volts, and the tach should give a 9.5 volt signal. So that's the first thing we need to check. So let's do it. Need to turn on a couple things. That one, this one, DC voltage. So what we got here, we have a Variac, and the Variac can go from 0 to 120 volts. I'm gonna plug it in. There you go. So this provides us, 120 volts AC. So that voltage comes to this bridge here, and it rectifies it. So the DC voltage is being fed to the motor, I got a speedometer attached that is showing the actual speed, and you can see the numbers running. They actually don't run, but the frequency of the camera and the refresh frequency don't like each other. This is called aliasing, that effect. Okay, so this guy measures the current, the motor current on the AC side, because this clamp can only measure AC current. And then I have one here. This measures the tach voltage, so that's the output from the tach. And then this guy measures the voltage on the motor, the voltage that goes into the motor. So let's switch it on. Okay, and I'm gonna go and turn this, and you can see the shaft coming alive. So that is really low speed. Okay, it's running 60 RPM. Okay, that's 60 revolutions per minute, so that's about 1 in a second. You can see it's really, really low. So what I'm gonna do is go up to 1000 RPM. That speedometer is lagging a little bit. I don't have a feedback loop going. It's pretty much I'm turning the variac and looking at the number, and it's got a little lag. So the motor is running around 970 RPM. It's jumping up and down. I'm not sure this tach is picking up the magnet properly. And we are reading 59.2 volts, so that checks out. And the tach is giving 9.47 volts, so that also checks out. In the same time, it's pulling about half an amp, low, really low current, and that's only enough to measure the idle speed of the motor. So there's no load, it's only just to spin the motor. So as far as it goes, the motor checks out. I'm not able to test it under load, so to put some kind of load on the shaft and then increase the load until we get a specific current. I'm not able to do that. So this is basically just free speed test. But as you can see, the motor is running pretty quiet and it's uniform, so it's not surging up and down. Again, the speed matches, the tach matches, and then the voltage matches. As far as physical size goes, the original motor is, you can see, 1585. That is in millimeters, so that would be 5/8. The second one I bought, which has the same part number, is 16 millimeters, right on the money. That is the same part number. And then the new one I bought, you can see it's 16 millimeters. There you go, 15.99, so 16 millimeters. So what I need to do is take the original flange and basically bore out the flange, this 5/8 size, bore it out to 16 millimeters. Now one interesting thing I found, check this out. This is the key that was on this new motor that I received, and this is a square key, and the size of the key, as you can see, is 5 millimeters. So it's 5 by 5 millimeters. It's a square key, and if you look, it is going to fit in a flange on one side. If I can focus, if you look, you can see it's going to fit on the flange on one side, but will not fit on the other side. So this side of the keyway is 5 millimeter, and then this side of the keyway is 3/16. So 3/16, just a little bit below 5 millimeter. But I'm probably not the first one playing with this. That's how this flange was done. So the first thing, I need to go and bore this out to the proper size, and there's a set screw here, so I'm gonna have to install a set screw and make sure it doesn't slide off. Well, that was a pretty intense machining process. First I did some dimensionings and drawings, sketches, put some dimensions on it, and then I laid it out in CAD. And so what I wanted to do is create a flange out of the two flanges. So as you might remember, this is the original flange from the motor, and you can see it's a square flange, and this is the flange that came on the new motor. And so my initial idea was that I'm gonna reuse this. I'm gonna just swap it out, and guess what, this diameter here where it meets the housing, it actually matches, but you can see that the bearing size is different. So this is 42 millimeter, the old one, and then the new one is 35 millimeter. Now, one option was that I can pull this bearing off and find a bearing that will match the shaft and the flange, but no. Another option was just to make a bushing for this one, and basically make an oversized bushing, heat this up or cool that down, press it in, and then finish the diameter on the lathe. So put it in a lathe, indicate on this diameter, finish it. I didn't want to go that way, and I tell you why. You can see clearly that the thicknesses are not the same. So the original flange is a lot thicker. So that's why I went to the length of drafting this up, and I put it in a CAD, and then I made sure that this is going to work. you know, kind of lay it out. It actually came out real nice. I didn't even try it on. I'm doing this video and I didn't try it on, and I'm so eager to do that. So there is a wave spring or wave washer that goes on the bearing like so, and then the housing just goes on like that. And I'm guessing that the tolerance between the bearing and the housing will be a little on the tight side. So I'm really eager to go and put these nuts back and mount the housing, see if it works, because then that's a big step forward, and I only need to fix 3 more things, maybe 4. Okay, it's bolted on and the shaft is spinning. It's turning nicely. The shaft is not locking up. There's a wave washer. So in every one of these motors there's a wave washer that is going to take the axial slack. You actually need to have an axial slack because this is aluminum, steel, aluminum. And so this has a different expansion ratio than the steel or the shaft. So when this heats up, the shaft it wants to expand, but the aluminum is expanding faster. So you always have a gap. So that's why you need that wave washer at the end. So the next thing is to make a sleeve for this end. Again, this is 5 millimeter. The encoder is 1/4 inch. And I also lay that out. So this is how it looks. So this is gonna be the flange that sits here, and then this is the encoder, and that's supposed to be a 7.3 millimeter size in between them. So the first thing is to create a flange that rests here. Basically it's a pipe, it's a tube. It's 5 millimeter on the inside and 635 on the outside, so 1/4 inch. But I either need to do a press fit here, so that 5 millimeter has to be 495. You know, even 50 microns is a lot of press fit for that. It really, I would need to bolt it on and press fit. So belt and suspenders. Because if that starts slipping, my encoder is gonna go off. You know, it's like the encoder is gonna be loose, and that's one of the failure modes. So I gotta make sure that whatever I do here is gonna be solid on the shaft. And then put the cover on, put the encoder, and then the last thing is bore this out. So this is the flange that connects the CNC, and this shaft here is 16 millimeter, and then the flange is 5/8, so 1585 supposed to be. So this doesn't go on. Made this little piece that will be the coupler between the 5 millimeter shaft here and the encoder. I'll save you from the details of machining. It's just basically turning. The good thing is that I had this 5 millimeter reamer. This is a Kyocera. I bought this years ago for a different project, but this is the thing. If you buy anything Kyocera, that's machining tool, that's top of the top. This fit is just amazing. You know, I don't think I ever done a nice fit like that. So obviously this is not a press fit. Here, if you if you look, you can see that as I applied it, it raised the oil level inside. There was some oil inside the hole, and it raised the oil. That fit is so good. It's by pure coincidence, but that's a real nice fit. So the next thing is, well, the first thing is I just want to show you that that fits here nicely, and then I can put the cover on. Okay, and then the encoder is gonna mate with this one, and it's a really nice fit. I was shooting for 635 on this one, and I measured this. It came out 6366, so it's 16 microns above the quarter inch size. But I guess I did one more pass on this one, and it's 625 now, so it's a 10 below. I might go and do another one. So this might be just a test piece. I was worrying about this section here because it's only 0.6 millimeters wall thickness, but it's pretty beefy, and I think it's gonna work. So the next thing, I'm gonna add 2 threaded holes here and use some grub screws to mount this to the shaft. So it will be just one more place where the encoder can get loose, but I will probably use some thread locker on it. That fit is really nice. Again, that's how it looks now, and you can see that it's got a real nice stack up. Check this out. I was shooting for 635. It's 632. But the first one was 620 something, 627. So I went back, made a new one. So this is the old one, this is the new one. They are basically identical, just this diameter is different. I don't know why, don't ask. So this one will sit there nicely. It's a really nice fit. Here's the encoder. It matches the encoder too. And there's no slop. I was wondering how much runout the shaft has. So this is a 10 micron indicator, half a thou. Half a thou. So it looks like it's got about 25 microns of runout. So 25 microns would be 1 thou. Let's see how much runout does it have with the coupler on. Here's the new coupler, and with the coupler on it has about double the runout. So 50 microns. And obviously this is not a ground surface, it's a machine surface, but I think it will work. It has no other choice, it has to work. I also found the instructions for the encoder. This is made by Renko, and 6000 RPM is the highest speed. And I did some research here. So it's 1000 ppm, 1/4 inch shaft, and then 5 volt is the excitation. This one also has the wiring. So it's got the wiring diagram. It basically gives the insight into that. So we got 5 wires here. So red is positive voltage, black is negative voltage. It's like MacGyver out of his playbook. And then channel A is white, channel B is green, and index or channel Z is the orange. So everything checks out. Everything is according to the data sheet. So I'm gonna go and I'm gonna hook this up to my oscilloscope. Why? Because I dropped it. I wasn't careful and I dropped it, and when it fell it bent one of these tabs. So I'm thinking that it fall hitting that tab, which, you know, this would attenuate some of the impact, but nonetheless I want to fire it up and make sure it works so that when I plug it back in, you know, I'm not chasing my tail, whatever. So I also worked on the business end, and I bored out the coupling, so I don't have to take out much. I also found the screw. This is M6. This is an M6 screw, but it uses 1/8 of an inch hex drive. So the 3mm is too small, 3.5 is too large, but the 1/8 size is a perfect match. So here's the key from the shaft. This is how the motor came. So it had this key. As you can see, it goes in nicely, and then the coupler just slides on. It's a real nice fit. There you go. Houston, we got signal, and if I change the triggering mode, so this is channel Z, you can see there's a nice signal. This is B, this is A. They are phase shifted side by side, so it's good signal. That is really good signal. That encoder is working perfectly. So time to assemble this bad boy back to the CNC. Alright, the motor is installed. You can see it right there, right above the spindle motor. So this is the Z stage, and now I'm in hand wheel manual mode, and you can see that it's moving down, it's moving up, moving down, moving up. So it's working. It's super quiet, it's not glitching, and I am really happy. Hope you guys learned something and enjoyed the video. If you like the video, please give me a thumbs up, and if you like the channel, please don't forget to subscribe. See you next time. Bye. Dum 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 dum.